Hi, everybody. Welcome to our first round of Fellows intro talks for this summer. First up is Seth. Seth's mentors are Jim and Ayana. Either of you want to introduce Seth?
Hi, yes. Wasn't prepared to do this, but yeah, so Seth started working with us a couple of weeks ago. And delved into it very quickly. I shouldn't try to do these things off the cuff. Yeah. What usually goes in an introduction. We're happy to hear from what has got. So please, please take away, Seth. I'm sorry.
Right.
Sorry.
Right, whenever you're ready, Seth.
Yeah.
All right. Thank you. All right. Hi, everyone. I'm Seth Bendigo, and today I'm going to be discussing refactoring awkward fourth generation in Uproot. And so just to start off, I wanted to do a quick intro into what Uproot is. So Uproot is an input-output library for reading and writing root files for use in Python. Right now it has more reading capabilities than it does writing. One of the benefits of using Uproot compared to using something like pyroot or rootnumpy is that it doesn't actually depend on root at all. And so that, along with Uproot being kept strictly a input-output library, means that it's very lightweight and portable. And so that's really useful. And so when using Uproot and when we get into reading in data types that are non-columnar, iteration is required just by the nature of it. And once we get to iteration, that means we have to use loops. And unfortunately, Python for loops are slow. Slow compared to compiled languages, I should say. And unfortunately, we can't use a compiled language at all because the byte for byte layout in the root files for these complex data types is just simply unknown at compile time. And so we need to read through the file to know what sort of data type we need to read in. Just-in-time compilation then could be used. That would be the next logical step, but unfortunately that would affect the portability of Uproot, which is something that we want to maintain. And so that leads into AwkwardForth. So what is AwkwardForth? AwkwardForth is an internal domain specific language for Uproot, and it is designed to it was designed to read in data into awkward array. And so using AwkwardForth and generating AwkwardForth code to read in the incoming data types, Uproot is sped up significantly. For the case of a 2D vector of floats, AwkwardForth is faster than Python by about a factor of 400, which is really significant. And so that's fantastic, but unfortunately, in its current implementation, we run into a couple issues that makes it very difficult to debug and maintain. The first big issue is that it's excessively mutable, and what we mean by that is as information needed to generate the AwkwardForth code accumulates as we read through the file, these Python objects will change their attributes in arbitrary ways that is very difficult to, when you're trying to trace back a problem, it's very difficult to follow what happened. And so that excessive mutability is something we want to avoid. Ideally, the code should be stateless or append only with the refactor. The other problem is just readability. There is dead code and a lot of nondescript attribute names that need to be cleaned up in the refactor. So And let's discuss the refactor. To fix these issues, particularly the main culprit, which is the excessive mutability, we're going to focus on making the code generation align more with functional programming. And so that will inherently avoid the mutability by the nature of functional programming, because we're focusing on pure functions with no side effects. We want to avoid as much mutability as possible. We may not be able to get it to 100% non-mutable, but the goal is as much as possible. This refactor of AwkwardForth is also going to utilize test-driven development a lot. There's already, what do I say on the slide, roughly 140 tests relating to AwkwardForth in the current implementation. And so just even starting off the ground, I can already use those to drive my development. So far, I've gone through the code base, which was a little difficult to learn coming in, but I'm still learning it, and that's been a lot of fun. I've identified and removed the sort of the boundaries of the AwkwardForth, all the areas that of the code that relied on AwkwardForth. I have been able to remove. So I have a version of the code right now where it does not use AwkwardForth code generation at all. It uses the pure Python implementation. And so my next step after is to go back to the version of the code that does have AwkwardForth, the current release, and understand in depth how AwkwardForth currently generates for a simple case, like previously mentioned, a 2D vector of floats. And then I can use that simple case as a jumping off point for redesigning the code generation. Right. Once I can replicate that simple case with whatever design I come up with, I can expand on that new design to cover other data types, and of course pass all the tests that are already written. And so that's sort of the guiding force in this refactor. And so, yeah, that's what Uproot is. That's what AwkwardForth is. That's what I've done so far, and that's where the refactor is heading. And that is all I have. Here are my sources. Is there any questions?
Thank you, Seth. Anybody have any questions for Seth? No question? All right. Nice presentation, Seth. Thank you.
Thank you.
Next up is Andrii.
Okay. So, hello. My name is Andrii. I am a graduated student from Tashchenko National University of Kyiv. My mentors are Enrico and Alex. And the goal of my project is the implementation of analysis grant challenge with RDataFrame. Thank you for inviting me to this talk. I want to start with a brief introduction to AGC. Analysis grant challenge aims to test at scale relevant physics analysis workflows envisioned for the high luminosity LHC, from data delivery to statistical inference. All different parts of the analysis pipeline can be implemented and executed separately to test many tools developed for HEP data analysis. And basically, AGC has two major pieces. The first is a specification of physics analysis task using open data, which reflects relevant workflows performed in analysis at LHC. The second is reference implementation, demonstrating the successful execution of this analysis task at scale. Currently, are being developed three implementations. The primary one is Coffee, made by Alex, and this project focused on RDataFrame implementation. The physics analysis task is top quark cross-section measurement. in a single lepton channel with CMS open data. This includes in particular top quark mass reconstruction, and the handling of systematic variation. Reconstruction of top quark mass is going via several main stages: data extraction, events filtering, and the calculation of observables. Events filtering aims to cut off all events without information relevant to the analysis. In the case of top mass reconstruction, the task is to choose events containing top quark decay products. Calculating observables may include a definition of custom quantities derived from columns contained in relevant events. In this slide is presented reconstructed top mass, and the decay point related to events filtering is that contribution from TT bar channel is much larger than from other concurrent channels. That means that selection of events is performed successfully. So selection of events relies on a single lepton decay schema, and according to the schema, the task is to select events with exactly one lepton, at least 4 jets, and at least 2 jets must be B-target. It means that the jet originates from B quark. The mass of the top quark can be restored by 3 jets, with 2 of them be B-target. So the second part of the algorithm is defining the trijet combination, which is assumed to be the decays product of the top quark per each event. These are 2 stages of analysis: selection of appropriate events and calculating observables. Here is an example of produced histograms. There are 2 regions with different selection criteria. The first one, signal region, aims to plot reconstructed top mass, and it uses explained above selection criteria with 2 B-target jets. And also analysis tasks include control region with only 1 B-target jet, and the observable quantity is sum of the transverse momentum of all jets in each event. The primary implementation is made by Alex, and my task is to catch up with Alex implementation, to do actually the same things and compare with his implementation. The ways how to discriminate signal events from the background and how to calculate observables can be slightly different. Analysis Grand Challenge evolved from a 0 version to version 2. And in each version, there are different data schemas used as input data, slightly different selection cuts, and slightly different ways how to calculate observables. During my last internship in IRIS-HEP, I have implemented root data analysis Grand Challenge version 0, but during this year, implementation, Coffee Alex implementation moved to version 2, and I am trying to catch up with Alex during this internship. So the task during my project is implement versions 1 and 2 with RDataFrame. During this internship, I already switched to new data schema. And currently I'm comparing produced histograms with obtained by Alex implementation. I have small discrepancies, less than 0.1%. And now I'm looking for origin of this discrepancies. I need to do some debug. And my next milestones are moving to new cuts, new selection cuts, and add machine learning component to calculate observable. And also everything needs to pass validation stage. That means produced histograms should be the same as in Coffee version made by Alex. That is end. Thank you for your attention.
Thank you, Andrei. Any questions? Do Enrico or Alex have anything they'd like to add about Andrei?
Yes, thank you. Absolutely. I just wanted to say we are very happy to have Andrei working with us again on this time not implementing the AGC for RDataFrame, but updating it to the latest spec. We have seen last year that Andrei has the right transversal set of skills that goes over coffee, root stuff, the physics involved in the analysis, and that a project like this is a win-win for a bunch. It's a win-win-win-win, right? For different sides of what we want the analysis scoring challenge to do. Because a separate implementation from the reference implementation, of course, brings up problems that were not visible before, brings up things that are underspecified in the docs, brings up the need to uniform things in make things more uniform in a way that other implementations can take advantage of those. So this is on the AGC specification side, and of course on the root side, it gives roots analysis interfaces the great feedback on what's nice, what's not so nice, and what should be improved. So very excited for this project, and of course Andrei already hit the ground running and is already hard at work.
Thank you, Enrico. Any questions for Andrei before we move on? No? Thanks again. All right, next up is Nazar.
So, hello, my name is Semkiv. I am a graduate student from the Russian National University of Kiev. The theme of my project is testing real-time analysis with LHCb, and my mentors are Mikhail Atseni and Professor Ilmet N. Smith from Massachusetts Institute of Technology, USA. So let's start with discussing, first of all, what is exactly LHCb detector. So LHCb experiment is one of the 4 large detectors at the Large Hadron Collider, which is LHC at CERN. And its primary purpose is to search for new physics through studies of TP violation in the case of heavy flavor argon. Although LHCb was designed primarily for precision measurement in heavy flavor physics, it also demonstrated some excellent capabilities in many other domains, for example, from electroweak physics to heavy ion and fixed target physics. So upgrade of the LHCb was designed with this wider physics program in mind as a general purpose experiment covering the forward region. And LHC has successfully operating from 2010 to 2018. And as I mentioned, it's a single arm forward spectrometer. To the left, you can see the layout of the upgraded LHCb detector. And it is primarily constituted of 2 parts. It has track and vertex reconstruction and particle identification trigger. And what is interesting about the trigger that the upgrade is the first one to incorporate fully software triggers. So let's discuss the trigger paradigm of LHCb a little bit more. So the objective of the trigger system is overall to reduce data volume. It reaches 4 terabytes per second because of the instantaneous luminosity in collisions to around 10 gigabytes per second, which can be recorded to permanent offline storage. So the reduction of this factor of 400 is kind of complicated, but because of the high rate of potentially interesting signals, and these signals can be at least partially reconstructed in the detector acceptance. And the instead majority of LHCb physics channels, they must be selected by the trigger by fully reconstructing and identifying the specific signals of interest. And this real-time analysis approach, or in short LTA, it was pioneered by LHCb in round 2, and it requires that the trigger performs a full offline quality reconstruction, which is enabled by calibration of the detector performed in quasi real time. And this results in a two-stage trigger system. So the first one is a inclusive stage, or which is also called high-level trigger HT1. It is based primarily on charged particle reconstruction, and this reduces the data volume by roughly a factor of 20. And the second stage, which is the HL2, which performs the full offline quality reconstruction or selection of physical signature. So to the left, you can see the online data flow the diagram, the place of RTA in it, and also you can see that we have HLT2 selections. They have been decided to select in this case both using turbo events and full events. So what is the difference between them? That the full events, they are more inclusive and they record all event information. They provide greater flexibility on the amount of information that needs to be saved. And also understanding them is fundamental to make a clear decision on what info do you want to say in the next type of event, which is turbo. It is much more exclusive line for the selection of specific case, and only part of the full information of the event is retained. And essentially by reducing how much info is stored, we might be able to collect more. So let's discuss the available lines. We use for full events, as I said, it is an inclusive expansion on more common feature of the case. So for the case which we are using, there are two main ones. So the topological trigger and the inclusive detached dilepton trigger. And for the turbo event, the main one is the dilepton trigger. And so the decays we are interested in is the decay of B+ to K+ GPTI and B0 to cluster 0 GPTI. And the reasons for this choice are various, but for example, they are expected to be easily selected in data. And what is peculiar that although these channels look very similar, they differ quite remarkably in their angular distribution. So what is our place in all of this? So overall goal is assessing the performance of this new trigger paradigm at LHCb because it is quite new. And so first of all, we are going to make a BDT-based machine learning algorithm to cleanly select decay candidates in 2022 data. After that, the decay the decay properties of the channels will be compared in the agreement with simulated data. And if needed, the existing trigger algorithms may be altered and improved, must be said. And if possible, we will also have a first look at the angular distributions of the calibration channel. So what is the timeline of work? So I started 1 week and a half ago. So currently we're in the stage. What is happening is the formalization with the idea behind the project, the usage of virtual environments in Bash, and Python scripting with focus on some statistical analysis libraries such as Sufit and VC. After that, we're going to develop some machine learning techniques to increase the purity of the signal events in data, and first fit to the reconstruct invariant mass of the Bendigo candidates and the familiarization with S4 techniques. So after that, there will be some data simulation comparisons and comparison to candidates selected with different trigger lines. And as I said, the trigger algorithms can be altered if necessary. And after that, there will be some parameterization of the distortion, which is caused by selections of the angular observables of the two channels of interest. And at the end, there will be first angular fits to the 2022 data. That is all. Thank you for your attention. Yeah, I will gladly answer any of your questions.
Thank you, Nazar. Any questions for Nazar? I was going to say, do Michelle or Luna have anything to add?
Can you hear me?
Yeah.
Yeah, no, I just wanted to say that we are quite happy that Nazar joined us. I mean, it has been only 1 week, but it's he has shown already, let's say that he's quite a fast learner. He familiarized quite quickly with indeed with Zfit and Uproot, and we were trying to perform already some first fits already in the first week. So in general, we are quite happy that he was able to join us.
Great, thank you. Next up is Atell.
I'm Atell-Yehor Krasnopolski from Terrestrial National University of Kyiv. This year, I'm working as an IRIS-HEP fellow on the project called Julia for AGC. So my mentors are Jerry Ling from Harvard and Alexander Held from UWM. Essentially, my project overlaps with what Andrii has shown, but I'm doing that with Julia. So I'm not going to talk about much about the technical details that Andrii already showed, luckily. So I'm just going to briefly describe what's Analysis Grand Challenge once again. Essentially, it's about performing the last steps in analysis pipeline and at scale to test the workflow sufficient for the LHC. This includes columnar data extraction from large data sets, obviously, processing of that data. We process that into histograms. That includes event filtering, construction of observables, evaluation of systematic uncertainties. That also includes, the essential processing of that data includes statistical inference and relevant visualization of these steps. So that should all be done in a reproducible way. And we also need to do that at scale. Here you can see some essentially the pipeline, but the full pipeline of the version 1.1, which got released recently, is that. So it also has some machine learning here. We're kind of skipping that part for now. So when I started like a couple of weeks ago, it was still version 1.0. Yeah, but we will get there a bit later. When it comes to essentially, when it comes to actual tests and comparing the results with something, then we are mostly taking the COFIA implementation as a reference. Yeah, I need to mention that we're also focusing on the TT bar analysis primarily, and we expect that to be implemented in Julia entirely by the end of the project. Now let's talk about why Julia, what's so good about it. So Julia is a programming language. It's a high-level programming language that's, it's advertised as perfect for physics and mathematics. It's basically fast by design, not with some packages, and it's JIT compiled. It has some nice interactions with other languages, but we're not interested in that for now in this project. And it's also proven to be efficient for high-energy physics. So you can see this organization, and I'm actually a part of that since last year. So last year I worked on Julia for jet reconstruction, and we had some nice results, essentially. So yeah, you can also find that here. You can also look on at this that website. It's quite recent, actually. It has some things and references to the papers that are published about Julia in high energy physics. There's also this paper, which actually only got released in June, I guess. So like this June, it's like super fresh. Yeah, and it also shows the progress so far with having Julia as a language for high energy physics. So essentially, that's a nice thing to go. That's a nice way to go, and we're trying to explore that direction a bit more by implementing the AGC pipeline in there. So let's talk more about the goals and status of the project. As I've mentioned before, the goal is essentially to have the AGC pipeline version 1.1, as well as some supplementary features implemented in Julia. So at first we'll skip the ML part, but that's kind of like a stretch goal. So that also includes exploring the possible designs and design solutions for the systematic uncertainties handling, which is kind of what we're dealing now already. And scaling that project up because we're we'll essentially be dealing with lots of data, and that needs to be operating fast. Yeah, we also need to run that remotely. So our progress so far, you can actually track that here. Here's a pre-rendered notebook, Julia notebook. This I took this from there. It doesn't show like every feature that we have for now, but it's good. You can look at it. We have some nice histograms already, but they actually, I mean, when I started, there was only one nominal histogram implemented. Right now we have both with different cuts. We also have some systematic uncertainties hard-coded into our project. So I mean, they work, but the design is not really that stretchy, and so it's not it's not going to be our final design. We're kind of thinking about something better as of now. Yeah, so it works quite well. We can actually go here. That's kind of a part representation. Here's the notebook. It only shows this for now. If you change this nominal with some actually basic, but already a lot of different variation types, you can get some other histograms, and you can also change the cut to 4J1B, which Andrii showed in his presentation and explained more about what that means. Yes, essentially that's what we have as of now, and hopefully we're gonna implement everything from the 1.1 pipeline by the end of the project. Thank you.
Thank you, Atell. Any questions? Enrico, you have your hand raised.
Yeah, I was curious, since the Julia ecosystem for high energy physics is newer than the Python ecosystem or the root ecosystem or the root stuff. Is there anything you feel is missing from the ecosystem? Are there major pieces that would be nice to have in order to implement the AGC, or everything, or all the ingredients are there, and this is going to be a demonstrator of how you put them together?
As of now, I haven't experienced any lack of ingredients in there. There might be something like last year when I tried to implement the jet reconstruction. The only problem I had was with the visualization, but we quickly solved that because essentially the package that I was using at the beginning just wasn't able to handle the diagrams that we needed. But that's like a very technical issue. I would say, well, I'm not the expert to ask here because I'm not really aware of what else is there in the Python ecosystem and what else is there essentially in the what else is needed in high energy physics in general in like that regard. So in the projects that I did and that I am doing right now, I haven't experienced that. And even if there is something that is lacking, it's probably being developed right now. So that's probably the answer.
Cool, thanks.
No problem.
Jerry or Alex, do you want to add anything?
I can imagine we run into visualization thing when we do very elaborate stack histogram or some kind of band plots at some point, which I don't think AGC has, but yeah, that would be one area which we lack for sure.
Yeah, perhaps just to add, I mean, it's great that we have this project, and me as a non-Julia expert, I'm super happy to be working here together with Jerry and Atell as two Julia experts to actually make this happen in practice. And I think the other aspect of that question is that we explore, I think, exactly that in this project, right? We will see what we run into and how well the provided functionality already works for doing something like this in practice. And I find it super exciting to see the same thing now implemented in various different ways, as we've seen in Andrii's talk and here in Atell's talk. So we can really compare lots of different approaches to the same analysis and get a bit better feeling for how they work out in practice, and be able to have a conversation on equal footing, which is why, yeah, I think these projects are very helpful. So very much looking forward to the progress here on the Julia end of things.
Okay, great. Next up is Lev.
Okay, so hello, I'm Lev Pambuk, currently a student of Odessa National University of Technology, and IRIS-HEP fellow for this year. I would like to present my planned work for this summer. It is software development for the Rucio Scientific Data Management system. My work is mentored by Martin Barisic and Mario Lasnik. So for start, I'll give you some context. Rucio is a software framework that provides functionality to organize, manage, and access large volumes of scientific data. So Rucio allows to spread data across globally distributed locations and heterogeneous data centers, uniting different storage and network technologies as a single federated entity. Rucio framework is currently in its development, and this development is pushed by LHC experiments that are taking a great volume of that data. And the planned modernization of the LHC will increase this volume to an unmanageable size. So new mechanisms and techniques are required to manage more efficiently storage resources and deliver data to processing endpoints. Goal for this project is to bring crucial developments to the common parts of Rucio shared by many communities and experiments. So my work will be focused on developing and solving current issues with source code. It includes client developments, operations, core, and transfer developments. So for the first week, it was just an entry week, basically getting used to a development environment. I was correcting typos in doc strings, removing link, and rearranging of imported statements, just basic work. Next is client development. It is improving error reporting during upload when reusing a deleted data ID. Fixing WebDev protocol state in order to return the data as specified, and fixing listing order of replicas. Next is operations developments. It is working on converting continuous in lifetime model exceptions to datasets, allowing to declare suspicious replicas by RSE and LFN. Next is code developments, which will be the biggest part of the project. It is adding parameters to diamonds, modification of RSE settings, adding size information to list rows, adding customizable replica sorter algorithm, and fixing headbits and points. And for the last part of my work will be transfer developments, which will consist of adding options to specify OpenID Connect token for communication with the storage element, development of dynamic bulk size submissioning to FTS. The planned timeline of my work is begin from 19th June to 3rd September.
Okay, thank you, Lev. Any questions for Lev? No? Okay. Thanks again. Next up is Ernest.
Yeah, 1 second.
I can also give a brief introduction if you want, Ernest.
Your pleasure if you want.
Yeah, fine.
Okay, so Ernest and I already had the opportunity to work on a project together last year. So we thought, why not do it again this year? Because it was very successful the last time. We are working again in the context of conditions data, and this time his project will be an intelligent caching system for the HSF inspired conditions database, which gained a lot of traction recently. But yeah, he will tell you all the details now.
Yeah, so I think I can start. Like, my name is Ernest, and as a part of IRIS-HEP fellowship program, I would like to tell you about my project, the HSF Conditions Database Intelligent Caching, and my mentor, as you know, is REANA. So let's get started from the condition data itself. So from the documents, you can read that conditions data is any additional data that needs to process event data. So we need to understand that every experiment had really valuable results, such as event data, like hits in the tracker, readout from the wire plan, etc. But to process this data, to work with it, to simulate, we need conditions data, such as temperature, voltage, current, and pressure. And this project is concentrate on this part, this valuable part of all experiments. So there are several challenges of them. For example, changes over time. We can repeat the vector calibration with larger cosmic data set, etc. And for this, we need to version and configure them. Also, there are different types of data. It could be like 3D map, time indexed value, single number, or also it could be granularity can rise. For example, if we have like structure, it has constant sizes and it's not changing in time, but some values can be run indexed. And we need plane agnostic by design of all this data. And one of the main parts of my project is high access rates. This one of the challenges that we're going to work on it. And the problem is that when we have conditions database, a lot of computers, like thousands of computers simultaneously having access request to the database, and these rates can be up to the kilohertz and more. So we need to invent the PICE database queries and effective caching to solve this problem, to make it effective, to make it optimized. And the similar challenges are for various HEP experiments. So to go deeply into solving these problems, we have HSF. So HEP Software Foundation is like a collection of people that are connecting in a forum format. They have their experience, and based on it, they're making like special documentation with the handling how to make condition data correctly. And it could be single database system for various HEP experiments. Also, if you want to see more, you can go on the link below and go deeply about implementation of this handling. You can see on the screen on the right side, you can see that database and the client side are separate and connecting only with the REST API interface. Just if we have one scientist that would like to download his payload to the store, he do it from the REST API. But we have two separate stores. In one store, we're saving only files of the payloads. It could be like 3D maps, time indexed, etc. So different format of data. But in the no payload database, we're saving only URLs to these files. And to make it clarify, there are already existing solutions to store payloads, but we're working only on the caching system into the no payload database for caching URLs. So about REST API, it's universal interface that using in the several types of challenges. This is one of the positive sides that is based on the HTTP protocol and simplified the requests, such as there are only 4 requests like get, post, put, or delete, that easy to understand for client. Also, it is stateless and cacheable. Go deeply into the project. I would like to show you an example of the log file. We gave it from the Nginx. And for the further work, we would work with the real data usage, like log files from the Sphinx production usage. And as you can see on the transcription of these log files, there are several features such as client IP, local time, type of request, URL address, and different features from for this URL address. And based on them, we're going to build to find the patterns of this request, find the perfection patterns, and also we need to understand that also request types implement in the solution, because it's very important for us. And on the screen, I can show like small visualization about how we're seeing this work in a simple way. Here you can see like simple patterns of cache and perfection, and on the line below, like where we have post requests, we can understand that when we have post request, our file that we have in a cache previously could change on the URL address. So the solution for now is like cache cleanup, but we understand that we can make it more with it, but for now it just stays as it now. Also, like small visualization, how we expect the response time would be using our cache system. It's very similar. It's very like easy way to visualize it, but I hope we hope that the response time would be smaller in a couple of times. I hope. And small talk about timeline. There are like few main points. Firstly, we're going to build plots, find the patterns on the raw data, because it's important to have something that we have that we can use on the further work for to have something that we can work with. Also, we trying to build different kinds of these plots because we have several features. It's important to understand how it works. And also it's work about different cache systems, how they could work, about different algorithms that we can use in our project. The next step, it would be like building and coding a real algorithm that could identify these patterns in the real time and build an optimized caching strategy. And one also bullet points to this is to compare this this solution to the already existing solution of caching. And if everything would be okay, I would like to download to the real system and try it in real time, like if it would be okay. So I think that's all for now. Thank you for attention. I hope it was interesting. Are there any questions?
Thank you, Ernest. Any questions for Ernest? Sam, you are up next.
Okay, maybe I can introduce Sam real quick.
Sure.
So Sam is a university student at Caldwell University. So just I guess a couple hours down the road from Princeton. Who's going to be working with myself, Lucas, Amy Roberts, and Jordan this summer on this REANA workflow for dark matter searches. And we're very excited about this because this is going to be hopefully an interesting project to help us expand our understanding of how workflow languages are working just outside of HEP in general, and also how to help us generalize workflow languages for the Analysis Grand Challenge and beyond. So without any further ado, Sam, please take it away.
Thank you, Matthew. So the project I'm going to be working as an IRIS-HEP fellow this year is implementing REANA workflow for dark matter searches. It's me, Sam Deo. I'm from Nepal, and my mentors are going to be Matthew Fickert, Lucas Henrich, Amy Roberts, and Jordan Stark. It's just about me and my experiences. Okay, so the fact that we all know about the laws of gravity is the greater the mass, the greater the pull, so that this can be seen in the orbiting of Jupiter's, because Jupiter rotates more quickly than Earth. As we can see that Jupiter takes only about 10 hours while Earth takes about 24 hours to rotate, and this is because of the Jupiter's more mass, and it travels through this space quicker than the Earth. And that's the idea that we will be implementing in learning about the galaxy rotation, because galaxies do not rotate the way we think. What we think is things orbit fast in center and much more slowly when we go far. However, what has been observed is the whole galaxy is rotating at roughly the constant speed, and it can be seen in the graphs, which are a little smaller in here, but yeah, the velocity is seem to be going down as we go far from the center. However, what has been observed is the velocity is almost or roughly constant even far away from the center. And these are the two simulation of the galaxy rotation curve. Sorry, give me a few minutes. Okay. So this is the galaxy rotation curve, which is just the velocity is just graphed in here, which is absorbed and expected from the luminous disk. As we can see, the velocity is not slowing as we go far. And this one is the green one is the observed galaxy rotation curve. And the analysis of this galaxy rotation curve can actually solve a lot of questions, because what we think is there are some kind of matter we cannot see, or light cannot pass. It does not have any effect of electromagnetic waves, so that is called as dark matter. And the analysis of galaxy rotation curve can be really helpful for solving these answers and getting answers to this question. And we will be implementing REANA workflow for the experiment. REANA is a platform for reproducible data analysis, and reproducibility and reusability in research and in computational data analysis is really important when it comes to using different operating systems, using different parameters, and in different experiments and in different data. So REANA is a platform which in high energy physics, it gives effective code reuse and data reuse platform. It has been extensively used for running containerized workflows for LHC experiments like Atlas, and for reinterpretation of published analysis. So our project aims to implement a REANA workflow for galaxy rotation curve fitting analysis to improve replicability and to provide a starting point for future work. And this is our timeline. We are in beginning weeks, and I'm just starting in July. So I'm working on getting to know more about galaxy rotation curve fitting analysis, and doing a literature review, and getting familiar with all the technologies that we'll be using. And that's it. Yeah.
All right. Thank you, Sam.
Thank you.
Any questions for Sam? No? All right. Thank you to all the fellows for your great presentations, and thank you for the support from the mentors. Thank you all else. Thank everyone else for coming as well. So that's it for today. So thank you.